All right, so now we're going to talk about momentum and impulse. So first with momentum. Momentum is a vector quantity, and it just equals an object's mass times its velocity. All right, so it's just the product of the object's mass and velocity. If the velocity of an object is 0, so if it's not moving, then its momentum is 0. All right, and the direction of momentum is the same direction as the velocity of the object. So if the object is moving north, then the momentum is also north. The units for momentum would be the units for mass times the units for velocity. Mass is kilograms, velocity is meters per second. So the units for momentum would be kilograms times meters per second. All right, so mass is kilograms, velocity is meters per second. Put them together, multiply them, you get kilogram meter per second. Okay, impulse. So if there is a force that lasts for a very short time, it's called an impulsive force. And the symbol for impulse is J. The impulse that the force delivers to an object is the area under the force versus time graph. Okay, so the y-axis here is force. The x-axis here is time. And if you were to find the area under this graph here, then that would tell you what the impulse is. Okay, J. All right, so how are impulse and momentum related to each other? So we're going to start off with Newton's second law. I'm going to write this all out on the side here. So we have F net equals ma. Okay, so how are we going to relate this? We're going to change this equation so it eventually relates momentum to impulse. Okay, so let's change our acceleration to the definition of acceleration. So acceleration just means the change in velocity over the change in time. Or another way of writing that is dv by dt. Okay, that's the definition of acceleration, is how fast is your velocity changing over time. All right, well, what is v here? Right, so dv by dt, if we were to take our m and our v and multiply those by each other, what does that give us? Okay, it's the same. We can take this m, the m is a constant, we can put it back in here if we wanted to, and we get dmv by dt. Okay, so all that we did was we took the constant that was there and we put it back in. Okay, just like if you were to say, what's the derivative d by dt of 2x squared? It's the same as 2 times the derivative of x squared. Right, that 2 is just a constant. We can bring it to the front, we can bring it back inside. It doesn't matter. That's all we did with the mass. Okay, so now what is this mv here? mv, we just said, was the definition of what momentum is. Momentum is mv. So now we have F net is equal to d momentum by dt. Okay, so that's what our F net is. So now what if we were to bring the dt to the other side? It's being divided by dt on the right side. If we multiplied both sides by dt, we'd get F net dt is equal to dp. Okay, so now what if we were to take the integral of both sides here? So if I'm taking the integral from t1, so from one time to another time, of F net dt, and taking the integral of the other side from one momentum, to another momentum, dp. Okay, well, what do I get? So the integral from one time to another of F net dt, well, that's the same as the impulse, because what this means right here is the area under the force time graph. And that's what we just finished saying was the impulse, right? The area under the graph over here, see, we said the area here is the impulse, J. So the area under the graph is J, is equal to the integral from one momentum to another of dp. So what's the integral of dp? Okay, this is just really, there's no number here, it's just like a 1, the integral of 1. Well, what's the integral of 1 when the variable is p? The integral would be p, right? So let's think about that again. So the integral, let's say, of x squared would be, you have to add 1 to the exponent, so x cubed, and divide by the new exponent. So that's the integral of x squared, plus you'd have to write some constant. But what if it was just the integral of a number, like 1? Well, what's the integral of 1? It would just be x. You always have to write down what the variable is that you're taking the integral with respect to. So since it's integral of 1 dx, it would be just x plus a constant. If it was the integral of 1 dp, it would just equal p plus some constant. Okay, but now what happens if you have these lower and upper bounds here? So if I have p initial and p final, that means that I have to take my p initial and p final and plug it into my p here. So I have p final minus p initial, and I don't need to put in my constant because when I subtract, they just cancel out. So when I take my integral of dp from p initial to p final, I just get p final minus p initial. All right, and so that's the same thing as just saying that j is equal to the change in momentum. All right, so now we have two different ideas here. We have j is the area under the forced time graph, and that's what's denoted right here. The impulse j can be calculated in two ways. It's the area under the forced time graph. Another way of saying that is that it's the integral from the initial time to the final time of f net dt. Okay, well that's fine. You would have a graph where you would be able to find the area under the graph. So it wouldn't be a curve like this. It would be a graph that has like straight lines and things like that. And you can divide the graph out into different segments so that you could figure out what the area under the graph was. Sorry, that was a horrible picture. Let me try a nicer one. So it looks something, let's say something like this. I wouldn't give you a curve because you can't really find the area under a curve very easily without using calculus. But let's say you had something like this, and this was your force versus time graph. Well then, if you wanted to find the area of that, you could always divide this. We could say, okay, well here's a triangle over here. So you can find the area of a triangle, base times height divided by 2. And then on this side we have a triangle and a rectangle, right? So rectangle length times width, triangle base times height divided by 2. So you can add up all of the areas to get the total area. So that's the first way to figure out the impulse, is if you are given a graph, you just find the area under the graph of the forced time graph. The other thing is it's also equal to the change in momentum. So if you know the initial momentum and the final momentum, or you know the mass and the velocity, initial and final, you could calculate your momentum. Okay? And like momentum, impulse is also a vector. So j is a vector quantity. The units are still kilogram times meters per second. All right, so same units, but there also can be written as Newton times seconds, and that's the more common way that we see it, because it's the area under a forced time graph. The units for force is newtons, the units for time is seconds. When you're finding the area, you're really just multiplying those units together to get newtons seconds. Okay, so those are the two ways that you can find the momentum, the impulse, J. All right, so now there's several questions that I'd like you to try out. I'm going to stop the recording here, but you can check the recordings for each of the video solutions for each question that you see in the lecture. All right, thanks a lot. Bye.